Next chapter, Electrochemistry. Now, in Form 2 on the chapter Effect of an Electric Current on Substances, we saw that ionic compounds conduct electric current in their aqueous or molten states. And that is because in their aqueous or molten states, they dissociate into free ions. We also said that in the course of conducting current, the ionic compounds are decomposed, and we called this process electrolysis. This kind of a setup is called an electrochemical cell. In this cell, the battery supplies electrical energy, which causes electric current to flow through the circuit. This kind of an electrochemical cell is called an electrolytic cell. Therefore, in an electrolytic cell, electrical energy causes chemical reactions. And so, you might wonder if the converse is true. Could chemical reactions produce electrical energy? And the answer is yes. In this chapter, we shall see how chemical reactions produce electrical energy and how electrical energy causes chemical reactions. Electrochemistry is basically the study of redox reactions. So let's start with that. Redox reactions and half equations. Consider a strip of copper wire dipped into a solution of silver nitrate. Over time, the solution turns from colorless to blue. We also observe a deposition of silver crystals on the copper wire. This is a single displacement reaction. The copper metal, which is higher in the reactivity series, has displaced silver in silver nitrate. The solution turns blue because of copper-2 ions in the solution. This is also a redox reaction, where reduction and oxidation are occurring simultaneously, and hence the term redox. Remember, oxidation means the loss of electrons, and reduction means the gain of electrons. So, for a redox reaction, electron transfer has to happen with one substance losing electrons and another substance gaining electrons. In electrolysis, a half equation shows us what happens on one electrode. So we need to complete and balance these half equations for the reactions. Remember, oxidation occurs at the anode and reduction at the cathode. The silver nitrate is an ionic compound containing silver and nitrate ions. So here is the equation again. All the ions shown separated. The copper metal has been oxidized because it has lost 2 electrons to form copper-2 ions. If we take out this half reaction, we now have a half equation. The silver ions have gained electrons to become reduced, represented by this half equation. They are called half equations because each represent half of the redox reaction. When the 2 equations are added together to form a final redox reaction, you can see that everything, including the number of electrons, are balanced. The electrons are equal on both sides of the equation and are therefore omitted. How about the nitrate ions in the original equation? Because the nitrate ions appear on either side of the equation in the same state, that is aqueous, they are called spectator ions because they have no effect on the overall reaction. Ionic equations only include species that have changed their states. For example, copper changes from solid to aqueous, and silver changes from aqueous to solid. One big challenge most students encounter is understanding the oxidation half equation. For the reduction equation, it's pretty straightforward that the species gains electrons, and so we have +2 electrons. But in oxidation, we said the species lose electrons, and yet we have a +2 electrons on this side of the equation. Why is that? Let's put it this way. If we were to take it literally that a copper atom loses 2 electrons, then we expect to have copper minus 2 electrons will give us copper 2 ions, right? Right. But conventionally, we don't write equations with minus signs. So we take these minus 2 electrons to the right side of the equation, and that changes to +2 electrons. It means the same thing. In order to understand redox reactions and the loss and gain of electrons, we need to understand oxidation numbers. The oxidation number is the apparent charge that an element has in a compound or the charge on an ion. Now, here is a set of rules for assigning oxidation numbers. Number 1, the oxidation number of any lone or uncombined element is 0. The same applies to molecules of the same atoms. And so potassium, aluminium, oxygen and hydrogen all have an oxidation number of 0. Number 2, for ions, the oxidation number is equal to the charge on the ion. And so sodium ion has an oxidation number of +1, magnesium ion has an oxidation number of +2, chloride ion has an oxidation number of -1, and oxide ion has an oxidation number of -2. Thirdly, in compounds, oxidation numbers are assigned based on the ions that each element would form using group numbers on the periodic table. So group 1 elements have an oxidation number of +1, group 2 elements have an oxidation number of +2, group 3 have an oxidation number of +3, and group 7 have an oxidation number of -1. But there are a few exceptions. The oxidation number of hydrogen in a compound is always +1, except in metal hydrides where it's -1. And so in hydrochloric acid, the oxidation number of hydrogen is +1, but in potassium hydride, it is -1. In sodium hydroxide, it is +1. Number 5, the oxidation number of oxygen in a compound is always -2, except in peroxides where it's -1, and in oxygen difluoride where it's +2. So in sodium hydroxide, the oxidation number of oxygen is -2, but in hydrogen peroxide, it's -1. In oxygen difluoride, it's +2. Number 6, in compounds, the sum of the oxidation number of all constituent atoms is equal to 0. Take for example sodium carbonate. In these compounds, there are 2 sodium atoms, 1 carbon atom, and 3 oxygen atoms. So we have 2 times +1 the oxidation number of sodium, plus +4 the oxidation number of carbon, plus 3 times -2 the oxidation number of oxygen. So we have +2, +4, plus -6, and if you do that, you will get 0. Calcium hydrogen carbonate. There is 1 calcium atom, 2 hydrogen atoms, 2 carbon atoms, and 6 oxygen atoms. So we have +2, +2 times +1, +2 times +4, +6 times -2. That gives us +2, +2, +8, plus -12. If you complete that, the answer is 0. Let's take an example. Calculate the oxidation number of manganese in potassium manganate 7. So in potassium manganate 7, there is 1 potassium atom plus 1 manganese atom plus 4 oxygen atoms, and that should give us 0. So plus 1, the oxidation number of potassium, plus manganese, plus 4 times minus 2, the oxidation number of oxygen should give us 0. So we have 1 plus manganese minus 8 is equal to 0. And the oxidation number of manganese is given by 8 minus 1, which gives us plus 7. Rule number 7. In ions containing more than one element, the oxidation number is equal to the overall charge on the ion. So a nitrate ion has an oxidation number of -1. An ammonium ion has an oxidation number of +1. And a carbonate ion has an oxidation number of -2. Let's take an example. Calculate the oxidation number of sulfur in a sulfate ion. This is the chemical formula for a sulfate ion. And so sulfur plus 4 times the oxidation number of oxygen should give us -2. So S plus 4 times -2 is equal to -2. S minus 8 is equal to -2. S is equal to -2 plus 8, and that gives us +6. Other redox reactions include reaction of a metal with an acid. For example, potassium reacts with sulfuric acid to form potassium sulfate plus hydrogen gas. Potassium is oxidized by losing an electron to form potassium ions in potassium sulfate. Its oxidation number increases from 0 to +1. Hydrogen, on the other hand, is reduced by gaining an electron to form hydrogen gas. Its oxidation number reduces from +1 to 0. Reaction of metals with water. For example, calcium reacts with water to form calcium hydroxide and hydrogen gas. Calcium is oxidized by losing 2 electrons to form calcium ions. The oxidation number is increased from 0 to +2. Hydrogen was reduced by gaining an electron to form hydrogen gas. Its oxidation number reduces from +1 to 0. Recall also that displacement reactions are also a type of redox reactions. For example, if a zinc rod is placed in a solution of copper 2 sulfate, a reaction will occur and zinc will displace copper from copper 2 sulfate. Zinc will go into solution and solid copper will be deposited on the zinc rod. This is the overall chemical reaction. Zinc plus copper 2 sulfate gives us zinc sulfate plus copper. For the ionic equations, zinc is oxidized to zinc ions by losing 2 electrons. Copper 2 is reduced by gaining 2 electrons to form copper atoms. The species that undergoes oxidation is called a reducing agent because it reduces the other. Zinc undergoes oxidation, and in the process, it reduces copper 2 ions. Therefore, zinc is a reducing agent, also called a reductant. The species that undergoes reduction is called an oxidizing agent because it oxidizes the other. Copper 2 ions undergo reduction and in the process, they oxidize zinc atoms. Therefore, copper too is an oxidizing agent. Generally, a more reactive metal will displace a less reactive one. This reactivity series helps us predict whether a redox reaction will occur. When a metal higher in the reactivity series is mixed with ions of a metal lower in the series, the atoms of the more reactive metal will push their electrons onto the ions of the less reactive metal. Consider when an iron nail is placed in a solution of copper 2 sulfate. A brown coating of copper is observed. Iron is more reactive than copper, so iron displaces copper from its solution. So a redox reaction takes place. Iron is oxidized to iron 2 ions, and copper 2 ions are reduced to copper atoms. Next, we have electrochemical cell. Now, consider a copper rod dipped in a solution of copper 2 sulfate. When a metal rod is dipped in an aqueous solution of its ions, some of its surface atoms lose electrons and go into solution as ions. The lost electrons, however, remain on the metal surface. The metal rod develops a negative charge, and this attracts the ions back again. Some of the ions accept electrons from the rod and form atoms once more. As the negative charge on the surface of the rod builds up, the rate at which the ions combine with electrons increases until eventually it is equal to the rate at which metal atoms lose electrons to form positive ions. At this point, an equilibrium is established. A potential difference is created between the metal rod and the positively charged ions in the solution. A potential difference always develops whenever there is a separation of positive and negative charges. The concentration of electrons on the metal rod is measured by a quantity called the electrode potential. This arrangement of a metal rod or electrode dipped into a solution of its ions constitutes a half cell. The half cell can be represented as metal-metal ion. The vertical line represents the phase boundary where a potential difference develops. For example, in this case, the copper half cell is represented as shown here. Now, the tendency of metals to form ions when in contact with their own ions differ from one metal to another. It is not possible to measure the electrode potential for a single half cell. However, half cells of two different metals can be connected to form a complete cell. This is because only the difference between the potential of the half cells can be measured. And so here we have a copper metal in a copper solution, and here we have a zinc metal in a zinc solution. If we let it sit like this, nothing will happen, and you will see that the voltage is zero. And the reason is that we haven't completed the circuit. To do that, we put a salt bridge. The salt bridge is often a filter paper saturated mostly with sodium nitrate. Once this is completed, the electrons will flow from zinc through the wires to the copper. In other words, from the anode to the cathode. And this is because the zinc electrode has a higher accumulation of electrons than the copper, and therefore an electric potential is generated. This type of an electrochemical cell, where chemical reactions produce electrical energy, is called a galvanic cell or a voltaic cell. In the course of time, we will make these observations. The zinc rod will wear out, while copper will increase in size. The intensity of the blue solution of copper 2 sulfate will decrease due to reduced number of copper 2 ions. A voltage of 1.1 volts is registered on the voltmeter. At the anode, oxidation takes place. Zinc atoms on the zinc rod lose electrons to form zinc ions. We can represent this half cell as shown here. At the cathode, reduction takes place. The electrons from zinc arrive at the copper electrode. On the surface of the copper electrode, copper-2 ions from copper-2 sulfate combine with the electrons to form copper atoms. This is deposited as copper metal on the surface of the copper electrode. The half cell can be represented as shown here. When the two ionic equations are combined, we have this equation. When the two half cells are combined, we have this cell diagram. The double vertical line here represents the salt bridge. In a cell diagram, the oxidation half cell is always written on the left. For example, write a cell diagram when an iron-iron 2 half cell is connected to a silver-silver ions half cell. The idea is to identify which between iron and silver is more reactive. Iron is more reactive than silver, so iron will undergo oxidation and silver reduction. If we start with an ionic equation, iron plus silver ions gives us iron 2 ions plus silver. The half equations are shown here. And so the cell diagram will be iron 2 ions, salt bridge, and then silver ions, silver. Next, standard electrode potential and the electrochemical series. Now, different combination of metals produce different voltages, and this depends on how strongly the metal could force its electrons to move across the cell. The electrochemical series is a list of metals and other substances arranged in a ranked order of how easily the atoms lose electrons. The far apart the metals are on the series, the higher the voltage produced across the cell. Electrons flow through the wire from the metal higher in the electrochemical series to the metal lower down. The electrode potentials are arranged according to the substance's ability to donate its electrons, that is, how easily they are oxidized. All values are measured in volts. You will notice that for hydrogen, the electrode potential is 0 volts. And that is because it acts as a reference. All other electrode potentials are measured against this value. This is a standard hydrogen half cell. It consists of a platinum wire that is connected to a platinum surface, which is in contact with an aqueous solution containing 1 molar hydrogen ions in equilibrium with hydrogen gas at a pressure of 1 atmosphere. Hydrogen gas is bubbled around the platinum electrode. In the molecular view, the platinum surface catalyzes the oxidation of hydrogen molecules to protons or the reduction of protons to hydrogen gas. At the electrode, hydrogen gas can either be oxidized to form hydrogen ions or hydrogen ions be reduced to form hydrogen gas. Therefore, 2 reactions are possible at the electrode: oxidation and reduction. The reaction is assigned a standard electrode potential of E0 equal to 0.00 volts and serves as the reference. To determine the standard electrode potential of any element, it is connected to the standard hydrogen half cell. So here, we have a zinc half cell connected to the standard hydrogen half cell. The electrons are moving from the zinc electrode to the hydrogen electrode, and so zinc is being oxidized. The voltmeter reading is 0.76 volts, and so the standard cell potential of a hydrogen zinc cell is 0.76 volts. The standard electrode potential of any element is taken as the difference between its potential and that of hydrogen. If the element has a greater tendency to lose electrons than hydrogen, the electrode potential of its half cell is negative with respect to the hydrogen half cell. For example, in this case, zinc has a greater tendency to lose electrons than hydrogen, and therefore its standard electrode potential will be calculated as follows. Ionic equations: zinc is oxidized to zinc ions. The standard electrode potential is 0.76 volts. Hydrogen ions are reduced to hydrogen gas with a standard electrode potential of 0.00 volts. Overall ionic equation is shown here, and the standard electrode potential is negative 0.76 volts. The cell diagram is represented as shown here. When the elements are connected to the standard hydrogen half cell, we obtain their standard electrode potential. This is called the electrochemical series. The electrochemical series helps us to compare the oxidizing and reducing powers of substances. For example, using the electrochemical series, can you predict the direction that electrons will travel for the following pairs of half cells? Remember, electrons always move from the metal with a more negative electrode potential to the one with the more positive electrode potential. So for A, electrons will move from potassium to hydrogen. For B, the electrons will move from zinc to copper. And for C, the electrons will move from lead to mercury. Just like the reactivity series, we can also use the electrochemical series to predict a displacement reaction when a metal higher in the electrochemical series is mixed with ions of a metal lower in the series. The atoms of the more reactive metal push their electrons onto the ions of the less reactive metal. We saw that when an iron nail is placed in a solution of copper-2 sulfate, a copper coating is observed. The higher metal in the electrochemical series is the one that always displaces the ions of the lower down metals. Metals lower down in the series cannot displace more reactive metals from their solutions. So why did the iron nail form a copper coating in a solution of copper-2 sulfate? Iron is higher in the electrochemical series, so it gave away its electrons to the less reactive copper-2 ions in the solution. The ion is oxidized as shown here. Copper is less reactive, so its copper-2 ions are forced to accept these electrons. So copper-2 ions undergo reduction, and as a result, copper metal is produced and coats the nail surface as shown here. The two processes happen simultaneously, and we call it a redox reaction. Now, using the standard electrode potentials on the electrochemical series, we can be able to calculate the EMF of a cell. Consider a zinc and copper cell. What will be the EMF? Now, the reduction potentials are as follows. For zinc, it is 0.76, and for copper, it is plus 0.34 volts. Now, the first thing to do is to determine which one is the strongest reducing agent. The strongest reducing agent is the one with the largest negative. In this case, it will be zinc. In other words, zinc will undergo oxidation. Now this is where the catch is. Remember, oxidation is the loss of electrons. But if you look at these equations, they are showing the reduction processes, that is, gaining of electrons. And we need this zinc equation to be in the oxidizing format. So we simply reverse it. Zinc gives us zinc ions plus 2 electrons. And because we have reversed the process, we shall also reverse the sign of the standard electrode potential. So now we shall have plus 0.76 volts. Copper remains the same since it will undergo reduction. So copper 2 ions plus 2 electrons gives us copper. The standard electrode potential remains the same, plus 0.34 volts. Now we add the two equations. We shall have zinc plus copper 2 ions will give us zinc ions plus copper. The standard electrode potential of the cell will be equal to 1.10 volts. Let's take an example. Calculate the EMF of the electrochemical cell represented here. The reduction potentials are as shown here. Lead is equal to negative 0.13 volts and silver is plus 0.80 volts. We identify the strongest reducing agent, that is the one that will undergo oxidation. It's the one with the largest negative. In this case, it is lead. The equation we have here is in the reduction form. So we reverse it and remember to change the sign as well. So lead will give us lead 2 ions plus 2 electrons. Standard electrode potential is plus 0.13 volts. Silver ion plus electron will give us silver. Standard electrode potential is plus 0.80 volts. To balance the electrons, we multiply equation 2 by 2. But the standard electrode potential remains the same. We do not multiply it. And that is because the standard electrode potential does not depend on the number of electrons. So we add the two equations. Lead plus silver ions will give us lead 2 ions plus silver. Standard electrode potential of the cell will be equal to 0.93 volts. Now, if you look keenly, you will see that the highest EMF is obtained when we combine the largest negative with the largest positive. The standard electrode potentials can also be used to predict whether or not a reaction will occur. And it's simple. If the overall standard electrode potential of the cell is a negative, the reaction will not happen. For example, predict whether this reaction will occur. Copper plus iron 2 ions equal to copper 2 ions plus iron. Given that these are the reduction potentials for copper being plus 0.34 volts and for iron being negative 0.44 volts. This equation suggests that copper displaces iron from its solution. So we want to predict whether that can happen. If we rewrite the half equations, copper undergoes oxidation to form copper 2 ions, while iron 2 ions undergo reduction to form iron. We go to the standard electrode potentials. In this equation, copper is undergoing oxidation, but this equation is that of a reduction process. So we reverse it. The standard electrode potential now becomes negative 0.34 volts. Ion remains the same. We get the overall, and we shall have copper plus iron 2 ions gives us copper 2 ions plus iron. Standard electrode potential of the cell is equal to negative 0.78 volts. It is a negative, and so the reaction cannot take place. Copper cannot displace iron because iron is more reactive than copper. And so in general, in galvanic electrochemical cells, redox reactions generate electricity, while in electrolytic cells, electrical energy causes chemical reactions. Now, uses of electrochemical cells. Electrochemical cells are used for generating electricity. For example, a dry cell is the simplest unit for generating electricity. It does so from chemical reactions and pumps electrons through wires. 2 or more cells form a battery. The dry cell consists of a graphite rod, which is the positive electrode or anode. The zinc container is the cathode. The electrolyte is a moist jelly-like paste of ammonium chloride enclosed in the metallic cylinder. A mixture of manganese 4 oxide and powdered carbon surrounds the graphite rod. The jelly is prevented from drying by sealing the top with a pitch. A cardboard washer is used to prevent the graphite rod from coming into contact with the zinc can. The zinc can is surrounded by an insulating thick paper covering. The positive terminal is a brass knob at the top, while the negative terminal is at the base. The reactions at the respective electrodes are shown here. The gases produced do not escape, but are immediately used up in other reactions. The hydrogen is oxidized to water by manganese 4 oxide. Ammonia forms a complex with the zinc chloride in the paste. A simple dry cell can produce a potential of 1.5 volts. When the cell is supplying energy, the chemicals are used up and therefore the cell has to be discarded. Such a cell is called a primary cell. In other words, it cannot be recharged. Rechargeable cells are called secondary cells, such as the lead acid accumulator. The main materials required to construct a lead acid battery are lead 4 oxide, spongy lead, and dilute sulfuric acid. The positive plate is made up of lead 4 oxide. The negative plate is made up of pure lead in soft spongy condition. The plates are then dipped in dilute sulfuric acid. Discharging process. When a load is connected externally, sulfuric acid dissociates into hydrogen and sulfate ions. At the positive terminal, lead 4 oxide reacts with hydrogen ions in sulfuric acid, forming lead 2 ions. At the negative terminal, lead atoms lose electrons to form lead 2 ions. The lead 2 ions formed react instantly with the sulfate ions to form lead 2 sulfate, which is insoluble and adheres to the electrodes. The net reaction that takes place is represented by this equation. As the battery discharges, lead and lead 4 oxide are depleted and the concentration of sulfuric acid decreases. Since the density of the aqueous solution depends on the concentration of sulfuric acid, measurement of its density can be used as a means of telling how far the battery is discharged. During recharging of the battery, the electrode reactions shown are reversed so as to restore the original reactance. And finally, fuel cells. Fuel cells are electrochemical cells which convert the chemical energy of a fuel directly to electrical energy. One important fuel cell is the hydrogen-oxygen cell. In this cell, the reactants are gases instead of metals. It has a positive anode, an electrolyte, and a negative cathode. At the anode, hydrogen ionizes to form hydrogen ions and electrons. The electrons are attracted to the anode and travel through it to an external connection. The hydrogen ions are attracted towards the cathode, traveling through the electrolyte. At the cathode, hydrogen ions, electrons, and oxygen combine to form water. The half cell will continue producing electricity for as long as the hydrogen and oxygen are supplied. Which causes chemical changes. The conducting liquid is called an electrolyte. It can be a molten ionic compound or an aqueous ionic solution. In either case, it contains free ions that carry current. Take an example of table salt. If you heat sodium chloride to over 800 degrees Celsius, it will melt. The liquid will contain free-floating positive sodium ions and negative chloride ions. Because there are only two types of ions, this is called a binary electrolyte. When the electrolyte is connected to a source of current, electrons will start to flow, creating an electric current. Consequently, the positively charged sodium ions are attracted to the negative electrode, and the negatively charged chloride ions are attracted to the positive electrode. Electron exchange happens, and this triggers a chemical reaction. Sodium metal is formed at the cathode, and chlorine gas is evolved at the anode. We say that the chloride and sodium ions have been discharged at the respective electrodes. Let us start with the electrolysis of water. This is an electrolytic cell used for electrolysis of water called a Hofmann's voltameter. Acidulated water is the electrolyte taken in the limbs of the voltameter. The electrodes, anode and cathode, are made of platinum and are connected to the positive and negative terminals of the battery, respectively. When current is passed through, water dissociates into hydrogen and hydroxyl ions. Hydrogen ions migrate towards the cathode. Here, they are discharged. In other words, they are reduced to form hydrogen gas, which displaces water downwards. At the anode, the hydroxyl ions lose electrons to form water and oxygen. Notice that for every 4 electrons transferred, 1 volume of oxygen and 2 volumes of hydrogen are produced. That is why the amount of hydrogen is always twice that of oxygen at any point in time. The discharge of hydrogen ions at the cathode reduces their concentration relative to that of hydroxyl ions, and therefore the pH level rises. Similarly, the discharge of hydroxyl ions at the anode reduces the concentration of hydroxyl ions relative to the concentration of hydrogen ions, and therefore lowering the pH. These counter processes ultimately ensure that the pH of water remains constant. And so, water is also a binary electrolyte because it contains only one cation and one anion. Now, consider an aqueous solution of sodium chloride. Apart from sodium and chloride ions, there are also hydrogen and hydroxyl ions due to the dissociation of water. So both hydrogen and sodium ions are attracted to the cathode, and both chloride and hydroxyl ions are attracted to the anode. The question is, which of the two ions will be discharged at the respective electrodes? We'll look at the preferential discharge of ions during electrolysis. Let us study the electrolysis of dilute and concentrated sodium chloride solutions and the products formed. We start with the electrolysis of dilute sodium chloride. When looking at an electrolytic cell, the first thing is to look at the ions present in the electrolyte. In this case, the electrodes are platinum rods. In the electrolyte, there are sodium and chloride ions from sodium chloride, and also hydrogen and hydroxyl ions from dissociation of water. The cations are attracted towards the cathode, while the anions are attracted towards the anode. So which ions will be discharged at the electrodes? As the electrons flow from the anode to the cathode, a redox reaction takes place. At the cathode, hydrogen ions with a reduction potential of 0.00 volts have a greater tendency to gain electrons compared to sodium ions, which have a reduction potential of negative 2.71 volts and are therefore preferentially discharged. They are reduced to form hydrogen gas. At the cathode, hydroxyl ions with a reduction potential of plus 0.04 volts have a greater tendency to lose electrons compared to chloride ions with a reduction potential of plus 1.36 volts and are therefore preferentially discharged. They are oxidized to form water and oxygen gas. Notice that for every 4 electrons transferred, 2 volumes of hydrogen and 1 volume of oxygen gas is produced. Therefore, the electrolysis of dilute sodium chloride is similar to the electrolysis of water. In addition, as hydrogen ions are used up in the cathode, the relative concentration of hydroxyl ions around the cathode increases, resulting in an increase in pH. Conversely, pH decreases at the anode as hydroxyl ions are used up and the relative concentration of hydrogen ions increases, causing the pH to fall. Therefore, the overall pH remains unchanged. And now let us look at the electrolysis of concentrated sodium chloride, also known as brine. Again, the electrodes are platinum rods. However, in this case, the concentration of sodium and chloride ions is much higher than before. At the anode, even though the hydroxyl ions have a greater tendency to lose electrons, the chloride ions are preferentially discharged owing to their high concentration. The chloride ions are oxidized to form chlorine gas. At the cathode, the same reaction occurs. The hydrogen ions are preferentially discharged over the sodium ions. they are reduced to form hydrogen gas. This is because despite their higher concentration, sodium ions have a very low tendency to gain electrons. Notice that for every 2 electrons, 1 volume of hydrogen and 1 volume of chlorine gas is produced, so the gas volumes are equal. As the hydrogen ions are discharged at the cathode, the relative concentration of hydroxyl ions increases, thereby raising the pH of the solution. The sodium and hydroxyl ions that remain in solution form sodium hydroxide. And so in general, a comparison in the electrolysis of dilute versus concentrated sodium chloride solution is both have the same species of ions in the electrolyte, but the concentration of sodium and chloride ions in brine is much higher. At the cathodes, the same reduction reactions occur. At the anodes, different oxidation reactions occur. The products formed also differ, with the electrolysis of brine producing chlorine gas and sodium hydroxide. Next, we look at electrolysis of dilute sulfuric acid. Now, a solution of dilute sulfuric acid contains 3 ions: hydrogen, sulfate, and hydroxyl ions. During electrolysis, hydrogen ions migrate to the cathode, while sulfate and hydroxyl ions migrate to the anode. At the anode, hydroxyl ions are preferentially discharged. They lose electrons to form water and oxygen. At the cathode, hydrogen ions gain these electrons to form hydrogen gas. So you see, for every 4 electrons exchanged, 2 volumes of hydrogen gas and 1 volume of oxygen gas are produced. So the amount of hydrogen is always twice that of oxygen. As you can see, the electrolysis of dilute sulfuric acid is similar to the electrolysis of water. Factors affecting the preferential discharge of ions during electrolysis. Now, we have seen that when 2 ions move towards the same electrode, only one can be discharged. There are 2 factors that determine which one will be discharged. 1. The position in the electrochemical series. Remember that cations undergo reduction. When 2 cations are at the same cathode, the one with a relatively larger positive reduction potential or the one with a relatively smaller negative reduction potential is preferentially discharged. On the other hand, anions undergo oxidation. When 2 anions are at the same anode, the one with a relatively smaller positive reduction potential will be discharged. And secondly, the concentration of the electrolyte. The ion whose concentration is higher will be preferentially discharged, but only if the 2 ions are close in the electrochemical series. Now, the product formed at the electrodes is also determined by the electrodes used. Let's study these using the electrolysis of copper-2 sulfate. We insert 2 carbon electrodes connected externally to a battery into a solution of copper-2 sulfate. We observe formation of bubbles, indicating a gas is being produced at the anode. When we remove the electrodes after some time, we notice a brown coating on the cathode. The copper-2 sulfate solution contains copper-2 ions, sulfate ions, hydrogen ions, and hydroxyl ions. When electrolyzed, copper-2 ions and hydrogen ions are attracted towards the cathode, while sulfate and hydroxyl ions are attracted to the anode. At the anode, hydroxyl ions are preferentially discharged, forming water and oxygen, which causes the bubbles. At the cathode, copper ions are preferentially discharged over the hydrogen ions. They are reduced to copper atoms and hence the deposition of a brown solid, which is copper. This reduces the concentration of copper-2 ions in the solution and thus reduces the intensity of the blue color of the solution and it turns pale. The relative concentration of hydrogen ions increases and therefore the pH of the solution drops. The same products will be formed if we used platinum electrodes. What if we used copper electrodes instead? The setup will be the same, and we have the same ions, copper-2, hydrogen, sulfate, and hydroxyl ions. When the switch is closed, copper-2 and hydrogen ions migrate towards the cathode. Here, copper-2 ions are preferentially discharged. They gain electrons to become copper atoms, which are deposited on the electrode that is the cathode. So its mass and size increase. Sulfate and hydroxyl ions migrate to the anode. However, none of them is discharged. Instead, copper atoms on the surface of the anode lose electrons and go into the solution as copper-2 ions to replace the copper-2 ions being discharged at the cathode. So over time, the anode loses mass and reduces in size. The amount of mass lost on the anode is equal to the amount of mass deposited on the cathode. Therefore, the concentration of copper-2 ions in the solution remains the same and thus the intensity of the blue color does not change. It is important you notice the differences in electrolysis of copper when inert and copper electrodes are used. And now, application of electrolysis. First is extraction of metals. Reactive metals such as sodium and aluminium are extracted through electrolysis. For example, aluminium is extracted from aluminium oxide through electrolysis. The aluminium oxide has to be made into molten by heating. The steel case is coated with graphite, providing the negative cathode. The positive anodes are immersed into the molten aluminium oxide and are also made of graphite. When electricity flows, the aluminium from aluminium oxide forms at the cathode and moves to the bottom of the tank where it's tapped off as pure liquid metal. Oxygen from aluminium oxide moves to the positive anode. It reacts with graphite, which is a form of carbon, to form carbon 4 oxide. The anode thus burns away and needs regular replacement. Electroplating. Electroplating is coating of one metal with another. Metals may be electroplated for beauty, protection, or both. For example, Jewelries are often coated with gold or silver. The electrodes and electrolytes are carefully chosen based on what metals we are plating with. If you want to copper plate another metal, you will use a copper-based electrolyte and have a copper anode. Copper for plating comes from the electrolyte solution, which is replenished by the copper anode. So if we want to copper plate brass, we shall have a copper anode, a brass cathode, and a copper-based electrolyte, that is copper 2 sulfate. Copper 2 sulfate solution contains copper 2 ions, which are blue-colored, and colorless sulfate ions. The copper 2 ions are attracted to the negatively charged brass cathode. They deposit on the brass, producing a thin copper plate. They do this by gaining electrons or undergoing reduction. The sulfate ions are attracted to the copper anode but are not discharged. Instead, copper atoms on the anode lose electrons to form copper 2 ions and move into the solution to replace the copper 2 ions reduced at the cathode. More copper 2 ions move to the cathode. Electrons are moving through the wire and reduce the copper 2 ions into copper atoms that coat the brass electrode. The copper anode gradually dissolves because it's losing copper atoms into the solution. So the concentration of copper 2 ions in the solution stays the same. If another metal was used as the anode, then the copper 2 sulfate solution would get paler because copper 2 ions are not being replenished in the solution. Purification of metals. This is also called electrolytic refining, which is a process of obtaining pure metal from an impure metal. The electrolyte has to be a salt of the metal to be purified. Here, we are trying to refine impure copper, so we use copper 2 sulfate. The impure copper has to be the anode. The cathode is pure copper. When current passes, copper 2 sulfate dissociates into copper 2 ions and sulfate ions. At the anode, copper atoms lose electrons to become copper 2 ions, which move into the solution. Copper 2 ions in the solution get attracted to the cathode. They gain 2 electrons to form copper atoms. The process continues. The anode loses mass and becomes thinner, and the cathode gains mass and becomes thicker. The impurities form below the anode and are collected as anode mud. Copper deposited on the cathode is pure copper. And finally, quantitative analysis of electrolysis. In this part, we shall see the relationship between the amount of substance produced and the quantity of electricity during electrolysis. It has been shown from experiments that the amount of substance deposited during electrolysis depends on the quantity of electricity that is passed. This is stated in Faraday's law of electrolysis. The amount of a substance produced during electrolysis is directly proportional to the quantity of electricity passed. Quantity of electricity Q is measured in coulombs. Current I is measured in amperes. 1 coulomb is the quantity of electricity passed when 1 ampere of current flows for 1 second. So quantity of electricity Q is equal to current I times time t. It has also been shown that 1 single electron carries an amount of charge equal to 1.602 times 10 to power negative 19 coulombs. So we can calculate the quantity of charge carried by 1 mole of electrons. We use the Avogadro's number, that is the number of particles in 1 mole of a substance. And so 1 mole of electrons carries 1.602 times 10 to power negative 19 times 6.022 times 10 to power 23. That is equal to 96,487 coulombs. This is called Faraday's constant, F. So if you take the electrolysis of copper, for every 1 mole of copper deposited, 2 moles of electrons are required. Therefore, it requires 2 times 96,487 coulombs to deposit 1 mole of copper, or 63.5 grams of copper. For iron, it will require 3 times 96,487 coulombs to deposit 1 mole of iron, or 55.85 grams. Let's take an example. Calculate the mass of copper in grams that would be deposited on the cathode when a current of 2 amperes steadily flows through copper 2 sulfate solution for 15 minutes. In our solution, first we write the equation. From this equation, 1 mole of copper is deposited using 2 moles of electrons. We calculate the quantity of charge. So 2 times 96,487. That gives us 192,974 coulombs. So 1 mole or 63.5 grams of copper requires 192,974 coulombs. Let us now calculate how much electricity was passed in our case. 2 amperes for 15 minutes. So Q is equal to I times T. That is 2 times 15 times 60. Remember, time has to be given in seconds. So that gives us 1,800 coulombs. And therefore, 63.5 grams require 192,974 coulombs. How much will 1,800 coulombs deposit? That will be 63.5 grams times 1,800 coulombs over 192,974 coulombs. The coulombs cancel out and we remain with 0.59 grams of copper. Another example. A steady current of 3 amperes is passed through copper 2 sulfate solution. Calculate the amount of time required to generate 500 cubic centimeters of oxygen gas at the anode. The molar gas volume at room temperature and pressure is 24,000 cubic centimeters or 24 liters. The Faraday's constant is 96,500 coulombs per mole. We start with the equation. From this equation, to liberate 1 mole of oxygen or 24,000 cubic centimeters, it requires 4 moles of electrons. So let us first calculate the amount of electricity that is. So 4 times 96,500, that gives us 386,000 coulombs. And so 24,000 cubic centimeters requires 386,000 coulombs. How about 500 cubic centimeters? That will give us 500 over 24,000 times 386,000. The cubic centimeters cancel out and we remain with 8,041.67 coulombs. And so, with a current of 3 amperes, how long do you need to pass 8,041.67 coulombs? Q is equal to IT, and so T is equal to Q over I. That is 8,041.67 divided by 3, and that gives us 2,680 seconds, and that is equal to 44 minutes and 40 seconds.